Welcome to AI Paper Podcasts. Today, we're diving into a really interesting paper that's shaking things up in large language model optimization. It's called DUPIO, that's DUPO, for Dual Learning-Based Preference Optimization. Comes from researchers at ByteDance Seed and Nanjing University, just out August 21st, 2025.
Yeah, and it hits on a fundamental problem, really. How do we get these LLMs to reliably check their own work, improve themselves, without needing tons of expensive human labels or those very specific verifiable answers? DuPO introduces this idea they call generalized duality.
Right, and this is the key takeaway right up front. This isn't just a small tweak, it's a genuine breakthrough. It lets LMs create their own feedback for all sorts of tasks, even complex ones that aren't easily reversible.
Exactly, and the big deal. We're seeing smaller, more efficient models using DuPO actually start to outperform much larger models at inference time. Think about that. A 7 billion parameter model beating one maybe 30 times bigger.
That's huge. We're talking serious gains, like over 2 points on Comet for multilingual translation.
And a solid 6.4 point accuracy jump in mathematical reasoning. It's really changing the game for LLM optimization.
So that's our mission today, Unpack DUPIO. We'll get into how it pulls off this self-improvement, why this generalized duality concept is so important for where LLMs are going, and what it means for you, whether you're in research or engineering. This could really shift how you think about self-supervision. Okay, so let's unpack this a bit more. Before DUPIO came along, getting LLMs to, really refine themselves properly was a constant struggle. What were the main roadblocks?
That's a great starting point. Understanding those hurdles really highlights why DuPIO is so clever. So historically, the main ways we improved LLMs, methods like RLHF or RLVR, they worked, but they all kind of hit a wall.
How so?
Because they all relied, fundamentally, on external supervision. Someone or something outside the model had to provide the right answer or the preference label.
Give us an example, like RLHF.
Exactly. Reinforcement learning from human feedback. Great for subjective stuff, making the AI sound more natural, more helpful. It aligns the model with what humans prefer, but let's be honest, getting humans to label all that data, it's super expensive, takes ages to scale up.
And people can disagree, right? Especially on tricky tasks.
Precisely. Consistency between annotators becomes a real problem. So it's a bottleneck. Cost, time, consistency.
Okay, so human feedback is tricky. What about using another AI, like an LLM as a judge?
Yeah, that was the next logical step, the LLM as a judge approach. Swap the human for another, often bigger, LLM, or maybe some fixed rules. It helped, definitely. But then you're just shifting the problem, aren't you?
How do you mean?
Well, the reliability now completely depends on the judge model. And those judge models have their own biases, their own blind spots. They can get fooled by, fancy wording, or even just the order you present the answers in.
So it's not always judging the substance?
Right. It might favor a certain style over actual correctness. It's like a biased referee.
Yeah. Gotcha. Okay, but what about tasks with clear right or wrong answers, like math?
For those, we had reinforcement learning with verifiable rewards, or RLVR. This uses the actual ground truth answer to give a simple reward, correct or incorrect. Much less human effort involved.
That's better.
It is for those specific tasks, but you still need those verifiable answers.
Yeah.
Getting those ground truths can be a bottleneck itself. And crucially, it just doesn't work well for open-ended things. Think about translation. There isn't just one perfect translation, right? Many versions could be valid.
Okay. So RLVR fails there.
Completely. So the common thread, the big limitation across all these methods, RLHF, LLM as a judge, RLVR, is this reliance on external supervision. It just fundamentally limits scalability and how adaptable these models can be.
Okay, so external supervision is the big bottleneck. The obvious next question is, can the model supervise itself? Which brings us to dual learning, right?
Exactly. Dual learning was this really elegant idea for self-supervision. It works by finding tasks that are kind of natural opposites, like mirrors of each other. The classic example is translation, English to Chinese, and then the dual task is Chinese back to English.
Okay.
So you pair this primal task and it's dual. The model can then generate its own feedback using something called cycle consistency. Basically, if you translate out and then translate back, you should end up pretty close to where you started.
And that means no external labels needed.
Precisely. That was the huge appeal, especially for things like low-resource languages where labels are scarce.
And this idea popped up elsewhere, too, not just translation.
Oh, absolutely. It was applied in cross-modal tasks like image to text and back using dual GANs. We saw it in knowledge reasoning, things like dual TKB, treating database queries and natural language questions as symmetric. It even got integrated into reinforcement learning. And yeah, for LLMs, there were earlier attempts like Trans0 and Dual Reflect, using back translation or similar ideas to refine outputs.
But, and this seems to be the crucial turning point, it wasn't the magic bullet for all LLM tasks, was it? It hit some serious problems when people tried to apply it more broadly.
You nailed it. That's exactly right. Despite the elegance, traditional dual learning crashed into two major roadblocks. When faced with the sheer diversity and complexity of tasks we ask LLMs to do today, these really broke that neat, self-contained feedback loop.
Okay, what was the first big challenge?
Challenge number 1. Limited duality in irreversible tasks. Simply put, most real-world LLM tasks just aren't perfectly reversible. Think about creative writing, summarizing a long document, or especially mathematical reasoning. The output the LLM gives you, well, it often just doesn't contain enough information to uniquely reconstruct the original input problem.
Can you give an example to make that concrete?
Sure. Remember the 3 plus 5 example. The LLM outputs 8. Now, try to build a Google task that only uses the number 8 to figure out the original question was, what is 3 plus 5? You can't.
Right, 8 could be the answer to loads of things.
Yeah, exactly. 10 minus 2, 4 times 2, square root of 64. That single number output is underdetermined, as they say. It doesn't uniquely point back to the input. And that lack of clean reversibility breaks the whole cycle consistency idea for many, many important tasks.
Makes total sense. The information just isn't preserved. Okay, what was the second challenge?
The second one was challenge 2, bidirectional competence asymmetry. Even for tasks that are theoretically reversible, like translation, LLMs often aren't equally good in both directions. A model might be fantastic at English to German.
But terrible at German to English.
Or just, significantly weaker. Maybe not terrible, but weaker.
Yeah.
And this imbalance, this asymmetry, creates really noisy feedback signals. Instead of helping, the weak dual task can actually penalize good performance on the primal task.
So if the back translation messes up slightly.
Right. Let's say the original was the quick brown fox, perfect German translation. But the back translation maybe translates the German word for quick back as fast. It's close, but not identical. The system might then wrongly penalize that excellent initial German translation because the cycle wasn't perfect.
Okay, I see. That noise would really mess things up.
It destabilizes the whole process. So these two issues, the lack of invertibility for many tasks and this competence asymmetry, even when tasks are reversible, they basically made traditional dual learning, well, as the paper puts it, ill-suited for general LLM optimization.
So this is where DUPIO comes in and does something different. How did Shuai Shi and the team manage to overcome these fundamental problems? What exactly is this generalized duality?
This is the really clever part. DUPIO essentially rethinks what duality needs to mean. Instead of insisting on this strict, full reversal of input and output, it does something smarter. It takes the original input, let's call it X, and splits it into two parts.
Okay.
X, which represents the parts of the input that are considered known, and Ju, the parts that are unknown.
Known and unknown components of the input. Interesting. How does that help?
Because the dual task, they call it the complementary dual task, TCD is designed only to reconstruct this U, that unknown bit. And critically, it does this using both the model's output, Y, and the known part of the input, XK.
I see. So you're not trying to reverse the whole thing, just reconstruct a specific missing piece using the answer and the parts you already knew.
Exactly. It fundamentally changes the objective. You're aiming for a much more constrained, manageable reconstruction target.
Can we use that simple math example again? A plus BC.
Perfect. Primal task. Given A and B, calculate C. DUPIO might say, okay, let's decide A is known, XK, and B is the unknown. The model calculates C. Now, the complementary dual task is, given the answer C and the known input A, can you figure out what B was?
Which is just C minus A equals B.
Right. B equals C minus A. And the reward signal comes from comparing B to the original B. See how much simpler that dual task is. It's not given C, what magical combination of numbers produced it. It's given C and A, find B. That known part, XK, acts as a powerful anchor.
That is clever. It seems to directly address those two challenges.
Absolutely. It hits them both. First, it overcomes the invertibility constraint because you're not demanding full reversal, just reconstruction of a chosen piece.
Right.
This works even if the overall task isn't strictly invertible.
Okay.
Second, it mitigates competence asymmetry. Because the dual task gets help from XK, the known part, it's much less demanding. XK provides context, narrows down the possibilities, and makes the dual task easier to solve reliably, even if the model isn't perfectly symmetrical in its abilities.
Which makes the feedback signal cleaner.
Much cleaner. And third, this whole approach suddenly makes dual learning broadly applicable. Tasks like mathematical reasoning, code generation, dialogue things that were previously problematic because they lacked strict symmetry or had complex conditional inputs now fit nicely into this generalized framework.
And the really neat part is a single LLM can run both the main task and this complementary dual task, essentially grading its own homework.
That's the beauty of it. It turns outputs directly into self-generated reward signals.
Okay, so we've got this really smart way to generate feedback without labels. How does DuPO then use this feedback to actually train the LLM to make it better?
So DuPO frames this as a preference optimization problem. The goal is to maximize the expected reward that comes directly from running that complementary dual task. Basically, how well could we reconstruct the unknown part?
And the reward itself can vary.
Yeah, it's flexible. For translation, they use things like BLEU scores to measure the quality of the reconstruction. For math, it was often simpler, like a binary reward. Did the reconstructed variable match the original exactly, yes or no?
And this plugs into standard reinforcement learning techniques. You mentioned GRPO earlier.
Yep, totally compatible. It works seamlessly with RL algorithms like PPO, proximal policy optimization, or as they used in the paper, GRPO, group relative policy optimization. You can think of these algorithms as the training engine. They take the reward signal from DuPO's dual task and use it to adjust the LLM's parameters, guiding it towards generating outputs that lead to better self-verification scores.
Why GRPO specifically?
GRPO is known for being pretty stable, especially when you're dealing with the massive parameter spaces of LLMs and potentially sparse or rule-based rewards, like the binary ones in the math tasks. It helps the model learn smoothly without going off the rails. The authors, just to recap, were Shuaiji Shi and colleagues from ByteDance Seed and Nanjing University.
Right. And what about the models they tested this on? Was it just one specific type?
No, they really went broad to show it wasn't a fluke. For translation, they used Seed X7B Instruct, which is ByteDance Seed's own model, already quite capable. For math reasoning, they used a real mix, smaller models like a 1.5B and 7B, distilled from DeepSeek plus Quinn 3.4B and Open Reasoning Nematron 7B.
And they compared against the big players.
Crucially, yes. They benchmarked against ultra-large models, including closed-source ones like DuPO, Claude Sonnet, the full DeepSeek R1, and even GPT-4o. This gives really valuable context to shows how much punch DuPO packs, especially for smaller models.
And the data sets.
Very comprehensive. For translation, 28 languages, over 750 directions, using samples from Flora's 200, evaluated with standard metrics like BLU, Comet, BLERT, plus human evals. For math, a mix of public datasets tested on tough benchmarks like AMC and AIM competition problems, looking at average accuracy. It's a solid experimental setup.
Okay, the moment of truth. What were the results? Did DuPO actually deliver these significant improvements?
Oh yeah, it delivered. Big time. Let's start with multilingual translation. Applying DuPO to that Seed X7B model, boom. Over 2 points gain on Comet, pushing the average score close to 65.
Impressive gain.
But here's the kicker. That 7B model, boosted by DuPO, started outperforming some of those ultra-large closed-source models, like DuPO and Quinn 3's 235B parameter model. It even matched the performance of DeepSeek R1.
Seriously, a 7B model keeping up with or beating those giants?
Seriously. And the human evaluations backed it up. It was performing comparably to GPT-4o and DeepSeek R1, and way better than Google Translate. It's a huge testament to the efficiency DuPO brings.
Wow. Okay, what about math reasoning? That seems like a really different challenge.
Consistent wins there, too, across the board. Open Reasoning Nematron 7B jumped from about 84% accuracy to over 90%. The Quinn 3.4B model got a really nice plus 6.4 point boost, hitting 83.6% average accuracy. And again, get this, that score beat the ultra-large DeepSeek R1 model.
A 4 billion parameter model outperforming DeepSeek R1 on math.
With DuPO, yes. Even the smallest model they tested, the 1.5B parameter one, saw a nearly 4-point gain. It just consistently lifts performance, regardless of the starting model size.
Did they check if it works on other architectures? Like, is it tied to the specific models they use?
Good question. They specifically tested this on the Llama family, too, using Llama at 3.18b and another called OctoThinker 8b. The results were just as strong, if not stronger. Llama at 3.1 saw a massive plus 24 percentage point jump in average score. OctoThinker had even more dramatic gains on specific benchmarks. So no, it definitely seems to be a general technique, not tied to one architecture.
You mentioned earlier it might even unlock potential in base models. Did they try applying it without supervised fine-tuning first?
They did. This is super interesting. They took a Quinn 3.4b base model, no prior fine-tuning for instruction following or anything, and applied DuPO directly. The model's ability to solve problems it saw during DUPIO training, measured by forward accuracy, shot up from just 15% to over 56%.
Okay, so it learned from the self-supervision. Did it generalize?
That's the crucial part. Yes, it did. On unseen test sets like AMC23, accuracy leaped from 20% to 70%. Huge gains on the A benchmarks, too. It's like DuPO awakened the latent reasoning capability that was already there in the base model, just untapped. That has big implications for training efficiency.
Absolutely. Less reliance on labeled fine-tuning data. Now, you also mentioned something about using this without extra training, just at inference time.
Right. This is another powerful application. Training-free inference time re-ranking. It's pretty straightforward. First, you get your LLM to generate several different possible answers or reasoning steps for a problem.
Okay, like beam search or sampling.
Exactly. Then, for each of those candidate answers, you use DUPIO's framework to automatically create a corresponding dual question. No labels needed, just based on the known-known split. You have the model answer that dual question.
So it's checking its own work for each candidate.
Precisely. You might even run the dual check a few times for robustness. Then, you just pick the original answer whose dual question got the highest score or accuracy. It's using self-verification as a quality filter after generation.
And this actually boosts performance significantly just by picking the best one.
Remarkably so. For Quinn 3.4b on the AM math benchmarks, this re-ranking process added 9.3 points to its average score, pushing it from 68% to nearly 78% without any extra training.
Wow.
And that score, again, surpassed ultra-large models like DeepSeek R1 and Claude Sonnet 4 Thinking just through smarter selection at inference time. The smaller 1.5b model saw an even bigger jump, almost 19 points. It's a really efficient way to boost performance at deployment.
Okay, those numbers are really convincing. But going back to the core mechanism, how critical was that specific strategy of splitting the input into known and unknown parts? Did they test what happens if you don't do that carefully?
They did, through an ablation study. It's a classic way to verify if a specific component of your method is actually doing the work. They compared the full DUPIO system against a version where they removed that strategic selection of the unknown component, essentially. They removed the data filtering that ensures good duality.
So they deliberately made the duality poorer.
Exactly. They wanted to see if that careful selection really mattered.
And the result?
A clear and significant drop in performance. Without the careful component selection, the 1.5b model performed 3.6 percentage points worse. For the 4b model, the difference was even bigger, 5.4 points lower performance compared to the full DUPIO.
So that confirms it.
Absolutely. It empirically proves that the generalized duality framework, specifically how you select that unknown component to ensure high-quality task duality, is crucial. It's not just an add-on, it's fundamental to DUPIO's success.
Can we look at a couple of specific examples from the paper? What really stood out to you in the case studies?
Yeah, the case studies really bring it to life. Let's take a math reasoning one. They had a geometry problem where the right answer was 468. The model also generated some wrong answers, like 108 and 312.
Okay.
DUPIO then created dual tasks. It did this by taking the problem statement and replacing some key numbers, like the circumradius, with variables, and then asked the model to solve for those original numbers, using the candidate answer, like 468, and the rest of the problem context.
So using the answer to reconstruct parts of the question.
Exactly, and here's the cool part. When they fed the correct answer, 468, into this dual process, the model was able to reconstruct those missing variables with about 69% accuracy. But when they used the incorrect answers, 108 or 312, the accuracy on the dual task dropped to 0%.
Wow. So DUPIO clearly signaled which answer was right, just by seeing how well it supported the dual task. No ground truth needed.
Precisely. It's true self-verification. The translation example was similar. They had an English sentence translated into two different Chinese versions. Then they back-translated both Chinese versions to English, the dual task. The first Chinese translation, which was actually good, high forward BLEU score, also produced a really good back-translation, high BLEU score. It showed the meaning was preserved. The second Chinese translation, which was poorer quality, lower forward BLEU, produced a terrible back translation, very low BLEU. It lost the meaning. Again, DUPIO's dual check automatically flagged the better translation without needing a reference.
These examples really drive home how it works. Okay, so let's try and sum this up. The big breakthrough with DUPIO is this idea of generalized duality. It lets LLMs optimize themselves without needing external labels by cleverly decomposing tasks and using a part of the input to help verify the output against another part.
Exactly. It breaks free from the limitations of traditional dual learning, where you needed perfect reversibility or symmetrical model abilities. DuPO makes self-supervision much more general and powerful.
And the impact seems huge. It's scalable, works across different tasks and models, boosts performance significantly both during training and even just for re-ranking at inference time.
Right. It points towards a future where LLMs can become much more autonomous in their improvement, reducing reliance on expensive data labeling or complex reward engineering. It's a really significant step forward for making powerful AI more efficient and adaptable.
It sounds incredibly promising. But like all research, there must be limitations or next steps, right? What did the authors mention?
Yeah, they were upfront about a few things. One is that the unknown component selection step, especially for math, can add some computational overhead during training.
Yeah.
Finding ways to make that selection process faster or maybe even learnable could be a future improvement.
Okay, what else?
Another point is that while they showed great results on models up to around 7 to 8 billion parameters, how DuPO scales and behaves on truly massive models, say hundreds of billions or trillions of parameters, is still an open question. Does the benefit continue to scale? Does it change? We don't know yet.
Makes sense.
And finally, most of the validation was on tasks like translation and math reasoning, which have relatively structured outputs. Applying DuPO effectively to more open-ended, creative tasks like generating long stories or holding truly nuanced open-domain conversations needs more research.
Good point. So wrapping up, let's bring it back to the listener. What does this mean for you listening right now? I mean, imagine a future where these incredibly complex AI models can continuously improve themselves, not just by throwing more data or compute at them, but through this kind of self-reflection, checking their own work using this generalized duality. What does that imply for how we design AI, how we train it, how we even interact with it? Could you apply a similar self-checking idea to niche problems in your own field? It really makes you think differently about feedback in AI, doesn't it? Something to definitely chew on.